Okay, this is the third in 3 lectures on acids and bases. This section is about oxides of metals and nonmetals, and then it'll be followed by doing some problems from this particular section about acids and bases. So the thing to know about the oxides of metals and nonmetals is how they react with water. So a metal oxide reacts with water and you get a metal hydroxide, a basic solution. So metal oxides make bases. Nonmetal oxides, on the other hand, react with water and they make acids. So nonmetal oxides make acidic solutions. Above, we have an example of a metal oxide. Here is a metal, magnesium, combined with oxygen, makes it for magnesium oxide, a metal oxide. It reacts with water and you get magnesium hydroxide, which we can easily see as a base because it has the hydroxide in it. This is an equilibrium reaction and it does favor the left. Now, nonmetal oxide is something like CO2. All nonmetals makes this a molecular compound. This is ionic, this is molecular. So carbon dioxide, when it mixes with water, you get H2CO3, which we can see is an acid. It's carbonic acid. So let's write a balanced equation for the ionization of nitric acid in water. So these are just some problems now from acid bases. So nitric acid, ionization in water. So we're going to put AQ. There are two ways we can write it. We can write it this way. This would fit more of the Arrhenius definition, where we see that it's a proton, it produces a proton in water. And if we want to go with the Bronsted-Lowry definition, we would react it with water. And we would show that you make H3O plus the hydronium ion, plus you would have nitrate ion left over. Okay, so there you go. Oxalic acid, which is found in certain plants, can provide 2 hydronium ions in water. Write balanced equations like those for sulfuric acid to show how oxalic acid can supply one for a second H3O. Now, if you go back to the previous lecture, you'll see that for sulfuric acid, we showed how sulfuric acid reacted with water. We did the Bronsted-Lowry. So we'll do the same thing here. And what we're going to do here is we're going to leave the states off for a moment, and I'll fill them in just a bit. So there's oxalic acid reacting with water. And so for the Bronsted-Lowry definition, what's going to happen here is this is an acid, so it produces something that has 1 less hydrogen and 1 less charge. This is the base, so it gets 1 more hydrogen and 1 more charge. So let me draw what happens to this. 1 more hydrogen and 1 more charge. So these are conjugate pairs because they differ by a hydrogen. And this will have 1 less hydrogen and 1 less charge. So what's a lesser charge than 0? -1. So there's the first reaction. And here's the second reaction. Okay, so you might want to try and do this on your own before you watch the rest. But this is the base, this is the acid. So I'm going to draw the product of the base first. And then this is going to have 1 less hydrogen and 1 less charge. So what's 1 less than 1? So what's -1 minus 1? -2. And there's your second reaction. So this is the Bronsted-Lowry version. Now, if we wanted to do the Arrhenius, we could. And for the Arrhenius, this is what we would do. Whoops. Cross that out. Cross that out. So you can see that we essentially leave the water out of it and leave the hydronium ion out of it. And this is what you end up getting. So it's kind of a shorthand of the Bronsted-Lowry. Okay. Write a balanced reaction of the basic oxide Na2O with water. So remember, this is a metal oxide, which makes a base. So we're going to take our Na2O plus H2O, and we're going to make a base. So what base can we make with sodium? And the answer is sodium hydroxide. Okay, let's try and balance this now. We have 2 sodiums, and now we have 2 sodiums. We have 1, 2 oxygens, 2 oxygens, 2 hydrogens, 2 hydrogens, and here you go. This is the reaction of sodium oxide with water to make sodium hydroxide. It's actually an equilibrium reaction. Okay, complete and balanced equations for the following acid-base reactions. Name the reactants and name the products. So first of all, we have to recognize that this is an acid and this is a base. This has only 1 proton in it, and this has 2 hydroxides. So therefore, to make them balanced, we need the same number of each. If I have 2 hydroxides here, I need 2 acids here. So how do I get 2 of these? I put a 2 there. Now, if I have 2 protons and 2 hydroxides, how many water do you make? 2. This should read solid, because it usually is. Okay, now we've accounted for the hydroxides, and for these 2 protons, what have we not accounted for? We haven't accounted for the magnesium. We haven't accounted for the acetates, and there's 2 of them. Now, is this going to be a solid, liquid, gas, or aqueous? Aqueous. How do I know it's aqueous? Because it has acetate in it. So here, how many protons do we have? 1. How many hydroxides? None. But for this ammonia, you pretend it has 1 hydroxide, because when it reacts with water, it produces 1 hydroxide. Okay, so with this one, it's really easy because the ammonia picks up the hydrogen, and you're left with this. And we could have simply written it this way. Instead of writing the ions separately. And this is the reaction. Write a balanced equation for the reaction of barium hydroxide with nitric acid. So here's barium hydroxide, which is interesting because it's soluble, somewhat soluble, with nitric acid. So here, this is the acid, this is the base, 2 hydroxides, 1 proton, not a match. If I put a 2 here, I have 2 hydroxides, 2 protons. That's a match, and that means we're going to make 2H2O. So what's left over that's unreacted? Well, let's look for the cation first. The NO3 didn't react. Is that a cation? Nope. The barium didn't react. Is that a cation? Yep. Okay, and the NO3, there's 2 of them. So this is how we write 2 of them. And this is going to be aqueous because the nitrate is soluble. Write an equation that describes the equilibrium that exists when nitric acid dissolves in water. Identify each of the 4 species in solution as either Bronsted-Lowry acid or Bronsted-Lowry base, and does equilibrium favor the products or the reactants? First of all, we have to know that this is a strong acid. So we have complete dissociation, or almost complete dissociation. So we want to know how this reacts with water. And here we have to think about this. Since this is an acid, it's going to donate a proton. So one less proton, one less charge. And this is a base, so it's going to get one more proton and one more charge. So these are conjugate pairs. And these are conjugate pairs. And remember, the conjugate pairs, the reason we like recognizing that is because they differ by one hydrogen and one charge. Okay, so does equilibrium favor the product or the reactants? Well, because this is a strong acid, it favors the products. Product favored because nitric acid is a strong acid. Okay, we have two more problems here. Write two chemical equations, one that shows H2O reacting with HBr as a Bronsted base, and a second that shows H2O reacting with NH3 as a Bronsted acid. So here we're going to put H2O as a Bronsted-Lowry base. So we're going to have HBr react with H2O. And since this is a base, it will accept a proton. One more hydrogen, one more charge. Since this is the acid, presumably, if this is the base, this is the acid, it'll have one less hydrogen and one less charge. And then H2O as a Bronsted-Lowry acid, we're going to react it with ammonia. Now, since this is a Bronsted-Lowry acid, it's a proton donor, so we want to draw one less hydrogen, one less charge. And here, one more hydrogen and one more charge. So there we go. And this is our last problem. Balance the following equations, then write the net ionic equation. So, first of all, if we take a look at this one, what do we think this is? I think it's a precipitation reaction because I have two ionic solutions reacting to make an ionic solid. This one, that looks like an acid, that looks like a base. So this is an acid-base reaction. And this one, gas forming. Okay, so let's balance these. 2 ammonia, 1 ammonia. We put a 2 here. 1 carbonate, 1 carbonate. 1 copper, 1 copper. 2 nitrates, 2 nitrates. Balanced. How about this one? Well, we have 2 hydroxides and 1 hydrogen. So I want 2 hydrogens here for 2 hydrogens, 2 hydroxide, and 2 water. And then what's left over is the lead and the 2 chlorines. Let's take a look at this one and see if it is balanced. Well, for this one, this is a tough one. We haven't really been introduced to this idea yet, the gas forming reactions. But in this case, what happens is hydrogen reacts with CO3 to make a carbonic acid. So I'm going to put a 2 here, and we'll see this later. And when I put a 2 here, we'll get 1 H2O and 1 CO2, and 1 barium and 2 chlorines, so this is balanced. Now, what does the net reaction look like? Well, we already know that for the precipitation reaction, you simply write the solid, and then over on the left, you write the ions that are aqueous that made the solid. So copper, 2 plus aqueous, plus carbonate, 2 minus aqueous. And you might wonder, how did he know that was a 2 plus so quickly? And the answer is, I can see there's one of each ion here, one copper, one carbonate. I know the carbonate's a -2, so the copper has to be a +2. So what is the net ionic here? Well, this one, you have to include the lead hydroxide, because in the net, you always include all solids and all liquids. So that means we're also going to have to include the 2H2O liquid. Now over here, are those two chlorines with that hydrogen, or are they separated? Well, because it's a strong acid, they're separated. So we actually have two chlorides. Here, this is a solid, so we have to write that in there. So here we have to write 2H pluses aqueous plus 2 chlorides aqueous. And there's your net. The net doesn't look any simpler than the actual reaction, does it? Okay. Now what do we do down here? The same thing. This, because it's a solid, comes down. This, because it's a gas, it comes down. It's not made out of ions. This, okay, so is this made out of ions? You bet. It's got 2H plus ions and 2 chloride ions. Is this made out of ions? You bet. Barium ion plus 2 chloride ions. So this isn't the net ionic, it's the total ionic. So let's get rid of the spectator ions. Remember, spectator ions are ones that don't change in the reaction. And you see these 2 chlorines here and these 2 chlorines here? They're aqueous before, they're aqueous after. They don't belong in the reaction. When we take them out, this is now the net. Okay, thank you for listening. And that was the last of the 3 lectures on acids and bases.